Hello students, now in class 11th I will tell you about the Carnot'S engine. Carnot'S engine. Carnot is the name of the scientist after whom this is called the Carnot engine. It is an ideal engine which was imagined by Carnot. This engine was never taken in actual practice. I have told you that the heat engine have the only function is that they have to convert the heat into the work. Parts of Carnot engine. It has the four parts. One is the source, at temperature T1. It is the source from which any amount of heat can be taken without affecting its temperature. Number 2, working substance. Working substance, it is an ideal gas. Ideal gas filled in a cylinder with perfectly conducting base and perfectly non-conducting balls. The a moving piston of perfectly non-conducting material is fitted in cylinder. There is no friction in piston and cylinder. And third part is insulating stent. Insulating stent. It is made of perfectly insulating material. And number 4, sink at temperature T2 less than T1, less than the temperature of the source. It can absorb any amount of heat rejected by working substance. So you see that all things here, they are ideal one. Perfectly conducting, perfectly non-conducting, frictionless. So this is all the 4 parts of the heat engine. So now I can visualize all these 4 parts like this. Here this is the source. Source at temperature T1K. This is insulating stent. and here we have sink, temperature T2K, and here this is the piston, here this is the ideal gas. Now this base perfectly conducting, and this piston frictionless, perfectly non-conducting. Non-conducting. These walls, this and this, they are perfectly non-conducting. Non-conducting. So these are the four parts of the Carnot'S engine. Now in this this is the perfectly reversible engine. It is reversible engine. Now we take its working, then we can say that this is takes place complete in 4 steps. Working. The one complete cycle has 4 steps. Number 1, isothermal expansion. Number 2, adiabatic expansion, and number 3, isothermal compression, and number 4, adiabatic compression. So thus there are 4 steps in one complete cycle. Initially what we have, the PV diagram. Here we take the pressure, here we take the volume, and this is starts from here like this, A to B, then like this, B to C. This is more steeper, and then like to this C to D, and then this is like this. This is the point D. So AB, isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. So here P1, B1 and T1, here P2, B2 and T1 isothermal, and this is your P3, B3 and T2 adiabatic, and then isothermal. So this is your P4, B4, T2, and then goes like this. So now you can have the area, we can make them like this, A, B, C, D. Suppose here we take E, F, G, H. So A, B, A to B, this is isothermal expansion, and B to C, adiabatic expansion, C to A, isothermal compression, or C to D, and then D to A. This is your adiabatic compression. So there are two expansions and two compressions. And initially the cylinder and the piston, the cylinder is taken in contact with the source. It absorbs the heat, and we say that when it has absorbed the heat Q1, then its pressure is P1, volume is B1 and temperature is T1. Then it is allowed to expand isothermally so that its pressure becomes P2, and then so in the first case it is taken in the contact with the source and this is allowed to expand because the energy will be absorbed from the source, so temperature will increase. So we have to expand the system. As a result, that there should be no change in the temperature, so pressure increases P2 and volume increases from B1 to B2. And then in second step, the system or the cylinder is taken in contact with the insulating stand. Then since the insulating stand is there, so there will be no exchange of heat. There will be adiabatic change. And when we expand, then the temperature will decrease, and we bring this temperature up to the temperature of the sink. And the pressure will be P3 and volume the V3. And this is again taken in contact with the sink. Here the system is allowed to compression, the temperature will increase, and therefore the necessary heat which is produced will be rejected to the sink, and then the temperature will remain to be T2 and pressure will be P4 and V4. Again the system is carried to the insulating stand, and where there will be no exchange of heat and the temperature will increase from T2 to T1, and pressure and volume will also be P1 and B1. Thus after one cycle, the burning substance returns to its original position. So there is no change in the internal energy of the system. So now step 1. the cylinder is taken in contact with source from which it absorbs heat Q1 to keep temperature T1 constant. The gas is allowed to expand. It is shown by curve A to B. So burden will be how much? Work done. This is suppose you W1, this is equal to the amount of heat absorbed. Since this is the isothermal, so whatever heat will be taken, that will be equal to the work done. So this is your nRT1 log E B2 upon B1. Step 2. The cylinder is removed from source and is kept in contact with insulating stem. The system is expanded adiabatically because no exchange of heat. Will not take place. The temperature decreases from T1 to T2. The P1, B1 becomes P2, B2 respectively. So work done. The curve BC B to C. Shows it. So work done will be W2 is equal to NR upon gamma minus 1 into T1 minus T2. This is now equation number 1, this is now equation number 2. And now step 3. Step 3. It is the working step. Working step. The cylinder is placed on the sink. The system is compressed isothermally, so temperature remains constant. The amount of heat produced in system is rejected to sink. So it is this step is shown by curve C to D. The heat rejected work done W3 is equal to Q2. Q2 is what? The heat rejected. The heat rejected. So this is equal to NR upon gamma minus 1 into log E, and the pressure will become P3 V3 on the system A to B, B to C, C to D. So B4 upon B3. Since there is compression, so this B3 will be less in comparison to B4. So we can write it to be minus NR upon gamma minus 1 into log E B3 upon B4. This is the amount of heat rejected by the source to the rejected by the system to the sink. So this is the W3. This is equation number 3. And now step 4. The P3 B3 become P4 B4 respectively. Now in this third step we have seen that the temperature of the system has decreased. So just to increase this temperature, it must be compressed adiabatically. Now step 4. The cylinder is kept in contact with insulating state. There is adiabatic compression which increases temperature from T2 to T1. The curve D to A shows this compression. This compression. The pressure, the P4 B4 become P1 B1 respectively. So after fourth step, the system and the surrounding returns to their original condition P1, B1 and T1. Thus, system and surrounding returns to original state after fourth step. Thus one cycle is complete. And it completes one cycle. So work done in fourth step, W4, this is equal to, since in this there will be the increase in temperature, so this is equal to your NR into T1 minus T2. So this will be taken minus nr upon gamma minus 1 into T2 minus T1. This is now 4. Fourth step, third step. So total work done. Total work done. W equal to W1 plus W2 plus W3 plus W4. So W1 is isothermal and T1 log E B2 upon B1. This is adiabatic, so nr gamma minus 1 into T1 minus T2, and this is minus nr T2 log E B3 upon B4. This is your minus nr upon gamma minus 1 into T1 minus T2. So now we can say that this term will cancel by this one. So we are left with this one, nr. We take common. This is your T1 log E B2 upon B1 minus T2 log E B3 upon B4. So this is now suppose the equation number 5. Apply an adiabatic equation of state Tv gamma minus 1 equal to constant. In adiabatic we have this T1 B2 gamma minus 1 equal to T2 B3 gamma minus 1. So this T1 upon T2 is equal to B3 upon B2 raised to power gamma minus 1. This is now 6. And again applying to this one, the second adiabatic curve. So that is your B1, B2, B3 and B4. So this is your T1 B1 raised to power gamma minus 1 is equal to T2 B4 raised to power gamma minus 1. So this T1 upon T2 is equal to B4 upon B3 raised to power gamma minus 1. This is the equation number 7. Equation number 7. So now from equation number 6 and 7, T1 and T2 are equal. So they must be equal. From equation 6 and 7. B2 B3 upon B2 raised to power gamma minus 1 equal to B4 upon B1 raised to power gamma minus 1. So we say that B3 upon B2 is equal to B4 upon B1, or B3 upon B4 equal to B2 upon B1. So in place of B3 upon B1, we will write down this B2 upon B1. Therefore, W equal to NR T1 log E B2 upon B1 minus T2 log E B2 upon B1. In place of B3 upon B4, we write down B3 upon. So the both term will be taken common. Log E B2 upon B1 into this scenario T1 minus T2. So this is what the work done. Now we will find the efficiency. Efficiency eta equal to W upon Q1, output upon input. So this is your NR log E B2 upon B1 into T1 minus T2 upon NR T1 log E B2 upon B1. So this NR will cancel and this log will cancel. So we will have this T1 minus T2 upon T1. Thus, W equal to T1 minus T2 upon T1, or 1 minus T2 upon T1. This is equal to eta. It shows that eta depends upon temperature T1 and T2. So this is about the Carnot cycle, and this is the how to find the work done, how to find the efficiency of the engine. So you like, share and subscribe this video, and also tell it to your friends who are studying in the same stream, and also tell to some other friends also. Thank you.